Good morning everyone. Today I am going to present a major review on acquired color vision deficiency. So it was published in the year 2000. It was published in the year 2016 by Matthew et al. Acquired color vision deficiency occur as a result of ocular, neurological, or systemic disease. Ocular in the sense it can affect the retina or the choroid. Neurological, optic nerve or the visual cortex, and systemic disease are diabetes mellitus. Different conditions may affect color vision ranging from the disease of the ocular media through to the pathology of the visual cortex. So mainly the color vision deficiency is secondary to ocular or visual pathway deficiency. It is known as acquired color vision deficiency. It was first recorded form of dyschromatopsia. So it is color vision deficiency is classified as congenital and acquired. Congenital color vision deficiency is said to be present from birth, whereas acquired color vision deficiency it is not present since birth. And congenital color vision deficiency is stable, whereas acquired is a progression or regression can occur in case of acquired color vision deficiency. Congenital is bilaterally symmetrical, whereas acquired is it may affect one or both eyes asymmetrically. It is thought to affect the entire visual field in case of congenital color vision deficiency, whereas acquired color vision deficiency may affect only a portion of the visual field. Acquired color vision deficiency is highly symptomatic. So congenital color vision deficiency is not that symptomatic. Acquired color vision deficiency has overall high prevalence than congenital color vision deficiency. Acquired color vision deficiency can be classified depending upon the site of pathology or by its clinical characteristics. Congenital color vision deficiency has predilection for affecting an individual cone class. Either red cone, S cone or the green cone can be affected. Whereas in acquired color vision deficiency it's a mixture. The substrate of color vision, so receptoral, any one color can be matched by mixing of three judiciously selected primary colors. So red, green and blue, by judicially mixing it, any other color can be matched. The physiological substrate of trichromatic color vision is the cone photoreceptors. There are three classes. The short is the S wavelength sensitive cone, M is the medium wavelength sensitive cone, L is the long wavelength sensitive cone. So the different class of cones have overlap. If you see here, the blue arch and the black, green and red, they have overlap but distinct at spectral sensitivity. The peak sensitivity lies at for short wavelength cone at 419 nanometers, for medium wavelength it is 531 nanometers, and the red long wavelength is 558 nanometers. The response of individual photoreceptor is unidimensional. So each photoreceptor sensitivity is unidimensional and cannot alone convey, a single photoreceptor stimulation cannot convey unambiguous information about the spectral nature of incident light. Because if I am seeing something, I am seeing so many things. So if a single photoreceptor is stimulated and it gives a signal, it does not mean the correct one. So there should be a large group of signals which convey similar stimulus. So called, it is a principle of univariance. Color vision is derived from a comparison of the rate of quantum catches. So it is nothing but a comparison of a rate of quantum catches signaled from the different class of cones. So the M and L cone share similarities in terms of their known histology, physiology and molecular genetics. Spectral sensitivity of photopigment is determined the protein portion of the opsin. So each photopigment has its own opsin, red, blue and green different. The M and L cone photopigments are coded on the X chromosome. You have to remember this. So M and L are on the sex chromosome, X chromosome, and S cone photopigment is coded on the chromosome 7. Post receptoral, there is an evidence to suggest that the processing of spectral information from the visual scene is conducted by a two subsystem of the color vision that are phylogenetically distinct. First, more ancient one system compares quantum catches in the S2, M2 and L cones, all the three cones. It's a quantum catch. And the second one is more recent system initially specialized for the spatial resolution. S-cone synapse with S-cone bipolar cells and with at least 4 different types of ganglion cells. So extensively studied for these is the small bistratified ganglion cells. In the last Tuesday class we have learnt about when there is an on excitation input from S cone. When there is an on excitation, there will be off excitation from the other cones, M and L cones with diffuse off bipolar cells. Ganglion cells subserving the S cone system synapse in the, so you have to remember this one also. Ganglion cells subserve the S synapse in the intercalated layer of lateral geniculate body. So both S cone as well as M and L cones will go to the lateral geniculate body, whereas this ganglion cell synapse in the intercalated layer of the lateral geniculate nucleus, and it gives input to the visual cortex at the layer of 3 and 4A. Whereas the information from the M and L cones is carried by the midget ganglion cells. So midget ganglion cells, so this center of the receptive field of midget ganglion cells, at least in the center. So the center of the midget ganglion cells from the central retina draws from a single individual cone, whereas from the periphery it draws from the multiple cones. So midget cells synapse in the parvocellular layer, whereas the S synapse in the intercalated layer of LGB, whereas the midget cell synapse in the parvocellular layer of the LG nucleus 3, 4, 5 and 6. This in turn goes to the visual cortex at the layer 4CB, whereas S goes to the layer 3 and 4A. This goes to the 4CB. So abnormal, these are the congenital abnormal color vision deficiencies. So anomalous trichromacy, dichromacy and monochromacy. What is anomaly? Pramod, what is anomaly? What is anopia? What is anomaly and what is anopia? Anomaly is the patient will be able to perceive all the three colors, but one color will be deficient. He will not be able to see red one as a red. He will see red as some other color. That is anomaly. Protonomaly, where L cone is affected, deuteronomaly green cone is affected. See LMS, red, green and blue. So deuteronomaly green cone is affected and tritinomaly blue cone is affected. It's a dichromacy. Dichromacy here is one color is completely absent. Anopia, protonopia. So red deficiency, deuteranopia green deficiency, tritopia blue deficiency. Monochromacy. Here the two colors are lost. Only one color will be there. So M cone monochromacy, this red and blue are lost. Only the green is seen. L cone monochromacy, M and S cones are lost. So only the red patient able to perceive. S cone monochromacy, here only patient will able to perceive blue color. So apart from these cones, there is one more, that is rod chromacy and incomplete achromatopsia. So even though the patient has lost all the three different kinds of cones which are specific, so patient will able to still see the color with the rod chromacy. Acquired color vision deficiency affect between 5 to 15% of the population. Of those diagnosed with acquired color vision deficiency, 66 had an acquired blue color. The triton is a blue deficiency. So blue is now after referred as S mechanism deficiency. S is the short wavelength blue. While the remainder acquired red and green deficiency, from now on it will be referred as M and L mechanism deficiency. M and L is the medium and long wavelength, green and red. Classification of acquired color vision deficiency. In 1897, Von Gries described three abnormalities of color matching. It is because of increased matching range where the patient is not able to identify the specific color, so reduce color discrimination. Either it is because of a shift match caused by a absorption system or a shift match caused by alternation system. So that is the altered sensitivity of the photopigments. Kollner indirectly spawned the rule which today bear his name. So what we know by a blanket rule is whatever the retinal disease, it affects the blue and yellow color, and optic nerve disease will affect the red and green color. This is the normal blanket we all remember, but it is not always correct. Multiple exceptions are there. Dominant optic atrophy produce blue deficiency, and numerous retinal diseases may cause red and green deficiency. So Variest is classification is the most widely used classification for acquired color vision deficiency. In this, he has classified into type 1, type 2 and type 3. So this is also important. From now on, all this color vision deficiency will be dealt as type 1, type 2 and type 3. So type 1 is the red green deficiency, type 2 is also a red green deficiency, type 3 is a blue color deficiency, that is a tritan. So here trichromacy, patient will have all three colors but defective one color. Monochromacy only single. Trichromacy three colors will be there, but mostly patient will unable to differentiate between proton and deuteron, red and green. So these two tests, Francois Munson 100 hue test and Rayleigh match test. These two tests he has conducted in almost more than 700 patients and come to a conclusion of this type color deficiency, type 1, 2 and 3. So if you see here, there is no defined axis in case of macular cyst and toxic amblyopia. The patient will not be able to pursue any specific color. So in the red and green, type 1 is the red and green deficiency in conditions of choroidal atrophic processes. Dichromatic red and green deficiency, example is the Stargardt's, and red and green deficiency, patient with optic nerve disease, optic neuritis, toxic amblyopia, chiasmal disease, chorioretinal degenerations, angioid streaks, myopic choroidal degeneration, rhegmatogenous RD, central serous retinopathy, chorioretinitis. All these conditions will have a red-green deficiency. And type 3 blue color deficiency we see in case of vascular retinopathies, diabetes, papilledema, glaucoma, dominant optic atrophy. So Variest observed that when acuity is affected by a disease process, when the visual acuity is less, automatically it is going to affect the red-green color. So because they convey the same pathway to the lateral geniculate body. So M and mechanism discrimination appears to be concomitantly disturbed. What is pseudo-proton anomaly? It is a form of altered system characterized by the Rayleigh match in which subject requires more red. So whatever the red color is there, it should be more intense red color to match with the subject, to match with the red-green mixture. So the patient will have a red-green mixture, and if you want to see a specific color, you should have a more red, more intense red to match with the yellow primary than a normal subject. That is pseudo-proton anomaly. Scotopization. Scotopization is intrusion of a red system under the photopic condition. So rod system will be in a scotopic condition, whereas in photopic condition, when the rod system comes into play, then in which the color vision tests are conducted, that is scotopization. Mary posted that the type of acquired color vision deficiency encountered was function of fixation, the fixation eccentricization theory. He observed that eccentric fixation could occur in patients with decreased visual acuity. Normally, when the patient will have more gross loss, decrease in vision, patient will have eccentric fixation, as we see in coloboma and all. So and he also further observed that in normal subject, prefixation threshold sensitivity measures mediated by the green and red cones decline, which those mediated by the S cones improved. Pincer elaborated on the finding of the Verist depth localization theory. He suggested that diseases of choroid and retinal pigment epithelium resulted in non-selective loss of rods and cones. So diseases of choroid and retinal pigment epithelium, here we don't see any loss of rods and cones, but the patient will have a color vision defect. And the inner retina or the optic nerve disease never demonstrated a cone damage or loss. So there is some overlap in the localization part of Pincer's depth localization classification scheme and Mary fixation eccentric theory. Indeed, these two later reconciled their classification system. A current interpretation. What is the current interpretation? Loss in the visual acuity implies impairment of the midget cell pathway specialized for the spatial discrimination, and it is superimposed on the system is a mechanism of specialized for the red and green color discrimination. So these two pathway goes together. Disease affecting this pathway will therefore be generally accepted to affect both spatial vision as well as red and green color discrimination. Conversely, disease selectively affecting the S cone and their pathway would not be anticipated to have any effect on the acuity or luminance contrast detection. So if the patient has a decreased vision, definitely red and green is affected. Where if the patient is having selective S cone deficiency, then patient will have a good vision. So why is S mechanism acquired color vision deficiency is more common? So blue color deficiency, why it is more common than red and green mechanism deficiency? So there are many hypotheses. The pseudo problem hypothesis, it says that certain tests are more likely to reveal S mechanism deficiency, as FM 100 hue test and D15 test. The scarcity hypothesis, in this a fixed proportion of all cone types are lost. So if the all fixed proportion all cone types of lost, in them the S cones, the greatest loss will be S cones because of their less number. The vulnerability hypothesis, the physiological and histological differences between S cones and their pathway and the other class of cones, these are more vulnerable in case of diabetic mellitus and glaucoma. The reduced rudency hypothesis, S cone system is devoted almost exclusively to the sense of color. So S cones are exclusively for the color with little contribution spatial and temporal resolution and contrast detection, whereas M and L cones are even for the spatial resolution, visual acuity. Aberrant adaptation hypothesis, certain tests place S system at an operational disadvantage. Example include using yellow high luminance background to test the styles mechanism. Mesopization filtered effect hypothesis, it was first applied to the color vision deficiency in glaucoma after it was observed that glaucomatous individual made similar FMH 100 hue errors to those made by the normal subjects under mesopic condition. So when there is a decrease in the size of the eye effective entrance pupil, it would cause a disproportionate loss of sensitivity in S cone mediated detection task. Absorption mechanism hypothesis, it states that many ocular diseases are associated with changes in pre-receptoral filtering. For example, many retinal dystrophies may affected with the cataract. So there are tests for acquired color vision deficiency. It is broadly classified into tests of discrimination, of matching, or of detection. So what are the tests of discrimination are? Pseudo isochromatic plate test. So in this we have vanishing plates and all those what Vasanthi has told. So what is the advantage is it's a capable of rapidly and effectively screening for red-green mechanism deficiency. Disadvantage is it cannot reliably distinguish between anomalous trichromacy and dichromacy. So it is poor at quantifying the severity of color vision deficiency. Tests may justifiable be used in conjugation with Shah-Green's saturation test in the assessment of acquired color defects. American Optical Hardy Rand Rittler, this test includes plates of red, blue, green and tetraran deficiency. Berson plate test specifically for differentiating S cone monochromatism from rod monochromatism. Ordering test. Ordering tests are Farnsworth-Munson 100 hue test. It was designed by the Farnsworth. So here previously there were 100 different colored caps were there. But later on what they have removed 15 discs were removed from the test to prove it with improved uniformity. So how many are remaining in Farnsworth 100 hue test? This is a quiz question. They will ask how many caps in 100 hue test. So this is the test of choice in detection and the diagnosis of acquired color vision deficiency. The D15 test was designed to dichotomize the color normal from the color deficient subjects. This is a popular test as it is easy to administer and can detect a wide variety of color defects. Only 15 caps will be there, 16 caps, so it will be easy to test the color vision defect. City University test and the Mullen refined test, it is a saturation discrimination test type. And Shalgren saturation test, it is developed specifically for use in patients with acquired dyschromatopsia and consists of 12 caps. These all are ordering test. Test for matching. So test for matching are Rayleigh match. It is described by the Lord Rayleigh in 1881 and is based on metameric matching principle. So by mixing monochromatic in a single specific wavelength like red, green light to obtain a match with the yellow color wavelength. Because of these primaries lies at the wavelength to which the S cone are extremely insensitive. This is the test of choice for detecting and diagnosing red-green mechanism deficiency. Computerized color test. It is an earlier test. They used color targets as gratings and spots. But the newer modulation in the color contrast of these targets were used to probe the subject color discrimination. So commercially available test is the Cambridge color test. Uses a C-shaped color target presented in neutral Stelling type array. The C itself subtends an angle of 4.3 degree and it gap at 1 degree with the subject, and he views the test at 2.4 meters. Pre-perimetric test or test of detection. These are the works of Stiles in the late 1980s. In this technique of the selective adaptation was first applied to isolate cone from the rod response. So this was the test to isolate cone response and rod response individually, but later it was used to isolate responses from individual cones, different kinds of cones. So it was modified by Wald who used broader band adaptive lights. So this is recently such tests are popularized for the assessment of so-called pre-perimetric glaucomas. It is a selectively adapting one cone mechanism will have no effect to the sensitivity of the remaining cone mechanism. So if one cone selectively adapted, it will not have effect on the other cones. Thus yellow background has been used to differentially adapt the M and L cone mechanism to study S cone. So yellow background is used to study red-green deficiency. Adapted red and blue color, red and green color mechanism to study blue color sensitivity. Similarly, a blue background has been used to study red sensitivity, and magenta background is used to study the green color sensitivity. Color vision in ophthalmic and neurological diseases. So this is an which color is deficit in which condition. Disorders of the ocular media. Implanted intraocular lens with the yellow tint modulated would not be anticipated to induce color vision deficiency. So you have seen yellow color tinted IOLs. So they do not anticipate induction of the color vision deficiency. Aberrantly, elevated levels of macular pigmentation may also induce or modify color vision deficiency. So when there is more pigment in the macular area, so it can also modify the color vision deficiency. Photoreceptor disorders, the cone dystrophies, photopigment defects. So in the family with the pedigree in which either the progressive or stationary cone dystrophy is associated, so in the early stage of the disease process, with either a proton or deuteron deficiency has been described. It was thought to have a causative defect in either the photopigment gene or their regulatory elements. Phototransduction defect associated with profound cone dysfunction. The alpha transduction defect has been reported in association with the phenotype resembling incomplete autosomal recessive achondroplasia, in which there was evidence of progression was observed in older individuals. Channelopathies. Defects in gene coding for both alpha and beta subunits of the cone in cyclic GMP cation channels has been implicated in the pathogenesis of complete and incomplete forms of rod monochromatism. In rod dystrophies or retinitis pigmentosa, we see a type 3 acquired color vision deficiency. What is type 3, Pramod? Which color? Blue. So blue color deficiency while vision is well preserved. Other retinal and chororetinal dystrophies. In congenital stationary night blindness, the patient with the severe deficiency tends to have red and green deficiency. Fundus albipunctatus. Color vision may be normal in the fundus albipunctatus, but some pre-degrees have shown that blue color deficiency is reported. Aguchi's disease. Color vision is normal. In gyrate atrophy, color is normal in early stages of chorioretinal disease, but it may be blue color may be affected in the as it progresses. Gyrate atrophy. Benign concentric annular dystrophy, blue color again affected. Choroidemia, red and green color are affected as the disease is progressed. Best or vitaliform dystrophy. In this blue deficiency is predominant in the early stage, and in the later stage red and green deficiency will develop. Butterfly pattern dystrophy. So in 100 hue test was normal until ophthalmoscopically observed visual changes are evident. So when there is a visual changes are evident, the color vision deficiency will be there, otherwise it will be normal. Downey's honeycomb degeneration, it is normal in early stages, but all the three colors may be affected in the late stages. In Stargardt disease, the type 1 acquired red-green deficiency will be there. In the later, which will be, there will be scotopization. So where the rods will come into play in the daylight. Enhanced Escon syndrome, it is here patient will able to read FMD 15 test plates and American plates, so no defect. Leber's congenital amaurosis, blue color deficiency that progress and involve red and green color defect over a period of time. Age-related macular degeneration, there will be blue color problem. Tritan discrimination is a blue color deficiency. Phototoxicity, there is no color vision deficiency. In retinal detachment, the blue color deficiency in patient with macula on. So there is a retinal detachment, but macula is still on. In that, blue color deficiency will be there. If the macula is lost, there will be a diffuse loss of color vision. In a CSR, patient will have a pseudoprotonomaly. Pseudoprotonomaly is where the patient should have a more red green match with the yellow. Patient in the early, and once the fluid is completely resolved, the patient will have a blue color deficiency. In diabetic retinopathy, 50% of them are normal, and some of 50 others have shown that. In optic nerve disorders, glaucoma first causes an acquired blue color deficiency. Then later a red and green color. Leber's hereditary optic, it's deficiency in prodromal sign. In optic nerve in mechanism, when achromatopsia induced dyschromatopsia. Stress 5 inhibitors, sildenafil. So it causes the disturbance of color vision, which are typically described as bluish tinge. So patient will pursue blue color. The patient who are using this phosphodiesterase 5 inhibitors in case of pulmonary hypertension or erectile dysfunction. Chloroquine or hydroxychloroquine, there is impairment preponderance to a red and green color, and all patient will revert an anti-arrhythmic but may cause a chromatopsia, typically yellow. Xanthopsia, patient will have a yellow vision. Environmental dyschromatopsia, toxins, exposure to organic solvent cause S mechanism, color vision deficiency, blue color. Have an affect the retina blue and red and green. Always in all conditions, there are few exceptions. So in the different stage and also checking the color vision deficiency is very important, because if they are the school going or college going children or students are not being checked with the color vision, then later on they come when they have an appointment or when they have written the completed the theory, and when they have an interview, then they come and we see that color vision deficiency is there for them, and they will be very upset about the future, because they have already decided that one has to become a pilot or some driver or in army or something or some industries. So they completely have to change their mindset and to